quizzes still out? Okay, well, can you finish up in the next 2 minutes, or do you? So if you look at Icon, there's a lab schedule. Oh, it lists all the sections. Yeah, you can yeah, it's in the PDF that has all the sections and times. Things listed. Okay. Thank you. All right, thank you. Okay. So today we're going to be putting to use all of these painful equations that we spent the last week and a half gradually deriving. And this is where sort of any fluid mechanics course is going to converge. Everyone is going to be using the Navier-Stokes solutions to solve a couple of classical problems. And so today what we're going to focus on is using Navier-Stokes to solve two kind of idealized problems, laminar flow between parallel plates and laminar flow through a circular pipe. So the idea of laminar flow is something I'll expand upon a little bit, but this is really, it simply means like smooth, continuous flow as opposed to turbulent. But we'll get into that more later. So as a quick recap, right? We've spent the last several lectures deriving really two equations that we use. First is conservation of mass, right, which we are framing as what we call the continuity equation. And this is written grad dot V is equal to 0 for incompressible flow. And we also developed, from conservation of linear momentum, the fabled Navier-Stokes equations for Newtonian fluids that are also incompressible. And in vector form, we write this as rho g minus grad p plus mu rho plus v So we're simply saying with this first equation that the flow cannot stretch or compress, right? That it's that in order for the density of an incompressible fluid to remain constant, or in order for the mass to remain constant in the system, its volume also has to remain constant. And the second one is simply a general expression for F equals ma, where we've got the gravitational body force, the surface force due to pressure, the surface force due to viscous shear stresses, and then our acceleration written as a material derivative. Okay, so I've written this in vector form, right? Because the idea with vector form is we can apply this to whatever coordinate system we choose. In general, we'll work in one of two different coordinate systems. The first being, oh, come on. There we go. The first being Cartesian coordinates, and these slides will be put online, so don't worry about copying this down exactly right now. But written in Cartesian coordinates, this is that vector expression. And then we've got conservation of mass written also in their Cartesian coordinates. So the idea here is, when expanded out like this, we've got four equations. Right? And we've got four unknowns, those being pressure, U, V, W. Okay? So this is technically a problem that we should be able to solve if we can figure out how to get through the complicated math. Written in cylindrical coordinates, things get messier because gradients, when working in cylindrical or any kind of polar coordinates, contain a lot of extra terms. So conservation of mass, and then conservation of momentum of Navier-Stokes in the radial component, the angular component, and then the z component. So this is a coordinate system, right, that looks like let's see. Trying to figure out how to draw this for you guys. Got R, theta, we have z. But the same, again, remains true. We've got four equations, okay, and if we count up the number of unknowns, we end up with four again, because we have the radial velocity, the angular velocity, and the z, or axial velocity, and then the pressure. Okay. So the problem is that, right, that the Navier-Stokes equations are these coupled second-order nonlinear partial differential equations, and in general, there's no way we can solve them for a universal solution. However, there are a few types of geometries that possess certain geometric features or simplifications that allow us to cancel out a whole bunch of terms for which we can actually obtain an exact solution. There are about 8 of them. One example being shown here on the right, the very slow moving flow between two parallel surfaces. Okay, so this is a video from experiments of a line of dye injected into oil, which then flows down under the influence of gravity and forms, it looks like a sort of parabolic distribution. So what we're going to do today is explore in particular this flow and this flow. So we'll get some practice with both the Cartesian forms of the Navier-Stokes equations and the cylindrical forms. So in general, to solve, we're going to establish sort of a template or a series of steps that we're going to go through whenever we encounter a Navier-Stokes-based solution. First step is always going to be list or write out all the governing equations in full form. And by that I mean take this vector equation right here and write it out in terms of the coordinate components. Okay, in terms of x, y, z, or r theta z. 2, list all simplifying assumptions. 3 is going to be using these simplifying assumptions to cancel terms in the governing equations until the solution is tractable. Okay, and usually this is going to mean until you have an ordinary differential equation for one of the quantities of interest. Right? And then 4 is going to be implement boundary conditions and solve for unknowns. All right, so give me guys a minute to finish writing these down. So we've got the two solutions or the two examples I want to go through in class today. I've got another thoroughly written out example that I'll post on Icon for you guys for kind of a different style of Navier-Stokes solution. But all of them keep coming back to these 4 steps because these equations are complicated and it's very easy to kind of get lost and not know where to start on them. So, first problem we're going to look at is problem of incompressible viscous flow between infinite parallel plates. So we've got sort of a slice in the xy plane of 2 plates parallel to one another, and the idea is that we're going to have flow ideally moving this way through between the 2 plates. Right? The flow is being driven by a pressure gradient of dp dx, meaning that the pressure is either increasing or decreasing along the direction of flow. So what we would be tasked to find in this problem is the velocity distribution across the gap between these 2 plates. In other words, what is the x component of velocity as a function of the y coordinate? I'll give everyone a minute to copy down the problem statement. Now, I will mention that when I say infinite parallel plates, what that means is essentially that they're infinitely long in the x direction and that they're infinitely long going into the page. Okay, and that'll have a ramification sort of in step 2 of the solution. All right, so going back to the solution process I sketched out, right? The first step is going to be listing the governing equations in their full form. So give everyone a second to get these copied down because we're going to start hacking away at them and crossing out terms as if our lives depend on it. Just a moment. So notice that we've selected the Cartesian versions of the Navier-Stokes equations, right? Those written in terms of x, y, z, quite simply because that's the way that the problem is framed, right? It's a problem that's sort of set up in rectangular space. We have flat plates. Okay, we haven't said anything about this being circular, and so this is one that lends itself to solving it in this 3-dimensional coordinate system with x, y, z. So we've got conservation of mass and conservation of momentum, respectively, written as the continuity equation and Navier-Stokes. So the next step would be step number 2. List all assumptions that we could use to simplify the problem. So the first assumption is we'll go ahead and say that we're going to assume that the flow is parallel to the plates. Okay. If we look here, we're assuming that the flow is just occurring horizontally. Right? So this indicates to us that v is going to be equal to 0. Right? That there's no vertical component of the velocity. Second assumption will be no flow into or out of the page. In other words, we're assuming that we've set up our coordinate system so that the x-axis points purely in the direction of flow, so that there's no flow along the z-axis now, which indicates that w will be equal to 0. Assuming that the flow is steady, and we're assuming, right, that the plates are infinitely long in the z direction, okay? And because of this, and because of the fact that we've lined up our coordinate system so that x points in the direction of flow, this also means that we can assume there's no variation of any of our quantities in the z-axis. In other words, it behaves like it's a 2D flow. Okay, so with these 4 assumptions laid out, let's go ahead and number these. 1, 2, 3, 4. I want to copy this. And step number 3 is going to be, right, canceling terms in the governing equations. So I'm going to repaste those governing equations right here. You all can use the ones you copied down earlier. But the idea is we're simply going to go through these assumptions one at a time and see which of these terms they allow us to get rid of. Okay. So up first, assumption number 1, right? If v is equal to 0, that means that anything involving v, right, including any variations in v, all also go to 0, right? Because what's the derivative of 0? 0. So we can cancel that out. We'll go ahead and number that 1, right? We've got a v right here. We'll cancel out, attribute that to 1. We've got a v here, 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 and here, as well as here, here, and here. And we'll cancel those all out and number those as 1s. Got a v there. Get rid of that. All right, assumption number 2. Right. No flow into or out of the page. In other words, w equals 0. Similar thing. Anything that's got a w, we'll cancel out and attribute that to 2. 2, 2, 2. Right? This one can be canceled out both due to 1 and 2. Cancel, cancel, cancel. And, oops, and a continuity equation. All right. Assuming that it's steady state, this means that what terms go to 0? Anything involving a time derivative. Well, these two have already been killed off, but this du dt term right here can now be eliminated. It's back to 3, and we'll go ahead and put 3's next to these as well, because if assumptions numbers 1 and 2 didn't get rid of them, then 3 would. And now if we assume that the plates are infinitely long in the z direction, okay, so we have no variation in z, this means that anything at d dz of any quantities now also go to 0. So that goes away. Assumption number 4, that goes away. Assumption number 4. We can add 4's to these cancellations. We can add a 4 to that one, a 4 to that one, and a 4 to that one. Okay. Now that we've used those assumptions to cancel out terms, we need to go back and inspect the problem and see what other kind of physical arguments we can make. For example, the way that the problem is drawn, if I just go up here, right? We've got G acting vertically, right, as drawn, only in the y direction, which is going to mean that the components of G in the x direction and the z direction also, we can take those to be 0. 0, 0. And there's one more simplification we can make, and this is going to require that we sort of iterate through. So at this point, we've implemented all of our simplifying assumptions and all of the information we were given for the problem. So the next thing to do is start working from top to bottom through our governing equations and see if we can eke out any more simplifications from inside of this set of 4 equations. And what I mean by that is, if we look at the continuity equation, at this point, this simplifies down to say that du dx is equal to 0. All right? Because we've canceled out the other terms. We'll go ahead and star this. So if du dx is equal to 0, what could we say about, for example, the second derivative of u with respect to x? Right? That's also equal to 0. So if we use that and we go through our equations, we've got this term right here that we can cancel out. We'll put a star by that. And we've got this du dx term right here that we can cancel out. We'll put a star on that. Okay. So whenever you're solving Navier-Stokes equations, this is what you want to see. Is you want to see a big set of equations with a lot of red slashes through it, because this is the only way that we can cancel out all those complicated, coupled, nonlinear terms that make them generally impossible to solve. So written out now, our simplified equations, right, would be dp dx, or negative dp dx, plus mu d squared u dy squared is equal to 0. Negative dp dy plus rho g y is equal to 0. And everything's canceled in z. Okay. So before we move on to step 4, I want to note that this right here, this expression right here, saying that du dx is equal to 0, is a special expression. This tells us that the flow is what we call fully developed. What this means is that, right, if the flow is moving in the x direction, but it's not continuing to change in the x direction, then it's reached sort of a spatial steady state. In other words, the flow on this end of the room is going to look exactly the same as the flow on this end of the room. Okay? This shouldn't be confused with the idea of steady state, right, where the time derivative is equal to 0. There's similar ideas, but they say different things, right? Time derivative means that it's not changing in time. this idea of fully developed flow, where it's not changing in the direction of flow, means exactly that it is stationary in space. Okay, so step number 4 is really divided into 2 parts. Okay, so we're seeking to solve for unknowns. In this case, the unknown is the velocity u. Right? The first step is going to be integrate our simplified equations. So we've got d squared u dy squared times mu. Let's go ahead and take this equation right here, right, and spread it out onto opposite sides of the equal sign. Okay. We can move, right, so what we're trying to find here is u. We're assuming that we've been given some quantity for the pressure gradient because we were told in the problem statement, right, the flow is driven by some pressure gradient dp dx. So in a problem like this, you'd be given a number, 1 Pascal per meter, for example. And we'll plug in some numbers once we symbolically solve this to see what it actually looks like. So what we're seeking to do right here is set this up as an ordinary differential equation. So if we move the viscosity over here, we just got a second order ODE, and we can integrate it twice to find u. Right? So we can say that d squared u dy squared is equal to 1 over mu dp dx. Integrating that once, dy is going to be equal to 1 over mu dp dx y plus a constant, right? Integrating it twice, 1 over 2 mu dp dx y squared plus c1 y plus c2. So we've got an expression for, we've got an expression for u, but it's not uniquely determined yet because we've got these unknown constants right here, c1 and c2. So in order to fully define our solution, and make it unique, we need to go through step 4b and implement known boundary conditions. So boundary conditions, right? I guess quick show of hands. How many of you have done boundary value problems before? Okay. So you've done ordinary differential equations, right? And generally, right, ordinary differential equations are often written in terms of derivatives on time, right? What happens when you integrate those? You end up with often 2 unknown coefficients as well, and you have to use initial conditions in order to fully resolve those coefficients, right? This is the same idea, but now we're just integrating on space. So it's exactly equivalent. It's just that instead of integrating on time, we're integrating on y in this case, and we have to know something about the flow, something about the velocity itself, u, or its gradient at 2 different points in the flow in order to fully define c1 and c2. So for example, right, if we've got, well, for this example, right, if we've got our parallel plates, okay, and we've got the flow moving between them, what can we say about the flow velocity right here at the wall? It's 0. Right? We've got a no slip condition. at y equals 0. Okay, and what can we say about it at the upper wall? Also 0, right? So we've got no slip at y equals h, right? We defined h as being the distance between these two blades. So those are our two boundary conditions. Okay. So boundary condition number 1, u is equal to 0 at y equals 0. Okay. So if we plug y equals 0 into this expression right here, we end up with is C2, right? So that fully defines C2. We've got that. C2 has to be equal to 0 in order to satisfy this first boundary condition. So we can check off C2. Boundary condition number 2, we say that u is equal to 0 at y equals h. So u of h, right, is equal to 1 over 2 mu dp dx h squared plus c1 h is equal to 0. So now our task is simply to solve for C1. So at this point, it's just more algebraic manipulation. And what we should get is that C1 is equal to negative 1 over 2 mu p dx h. So now all that's left is to plug in our values of C1 and C2 into our general expression for U, right? Our general solution, and simplify it however much we need to. So plugging C1 and C2 into Y, we end up with over 2 u dp dx y So, for example, so I didn't give us any values for like dpdx or the viscosity, simply because I wanted to concentrate on going through the symbolic derivation of this first. So, right, at this point, it's pretty trivial to say, you know, for example, what if we're dealing with something that has a dynamic viscosity of 1 times 10 to the negative third Newton second per meter squared. Okay, so this is water-ish. Say that h is equal to 0.1 meters, and this whole thing is driven by a pressure gradient, dpdx, to negative 100 pascals per meter, right? Which is going to end up yielding units of negative 100 newtons per meter cubed. Well, at this point, if we plug all of these in, it's really quite simple to come up with a formula for U. And if we plotted that out, We'd end up with something that looks like this. Oops. Okay. It's going to be a parabolic velocity distribution with a maximum of 125 meters per second. And so then, for example, if we said to compute the flow rate between the two, across a certain area, you have all of the numbers necessary to do so. So this is the very guided example. I'm going to throw in a twist now and see whether you guys. Oh wow, we're almost out of time. Going by quick. For me, probably not for you guys. You got this. All right, so we'll quickly do one little variation on this, or talk through the variation, and then I'll post the cylindrical coordinate version on Icon. Just understand that, right? It's exactly the same process. Okay, it's just using different, coordinates, but the integration and the process is going to proceed exactly the same. So, what if this same problem, right? Instead of having two fixed plates, what if the bottom plate was fixed, okay, and the top plate was getting dragged along with some velocity of u1? Questions? Does this change any of our simplifying assumptions? So if you look back at our list of assumptions, basically the flow is two-dimensional, there's no vertical velocity, no velocity into the page, that it's steady state, and what was our other one? And that there's no variation in the z direction. Yeah.
So we assumed that the fluid at the top plate was 0 because the top plate wasn't moving. Now it's going to be moving at that velocity.
That's what I'm getting to. Yeah. But but of those four assumptions, right? 2D flow, steady, and no variation going into the page. Is there anything that I've drawn here that gives you any reason to change any of those? No. Okay. So does it change any of our simplifications or simplified governing equations? Okay, that we right? Any of the cancellations that we made to the Navier-Stokes equations? Well, if it doesn't change any of our assumptions, right, we should be able to make all of the same cancellations based on exactly the same justifications. Okay, so no. It's not until we get to our boundary conditions, okay, that we have to say yes, something changes. Because we can restate our two boundary conditions now as u equals, or if we say u of y at y equals 0 is going to be what? It is if our x, y, right? It's still going to be 0. And u of y at y equals h now is going to be what? Right? The no slip condition still applies, right? So down here where the wall isn't moving, it's stuck to the wall, the velocity has to be 0. Up at the top, it's stuck to the wall, so it has to be moving along with the same velocity as the wall. We would say u1, okay? we would use these two boundary conditions to solve for C1, C2, and we would then plug those in to get a unique solution, u function of y. Okay, so I'll post those examples. We'll spend some more time on Navier-Stokes on Friday. This is the last, by the way, this is the last bit of information that's going to be on the midterm next week, right? Idea of simplifying Navier-Stokes, implementing boundary conditions, etc.